Hey, what's up, everyone? Good to see you here. Just chilling out. Got my coffee, second round of coffee. What questions are there to start off? If you're here, say hey. Let's throw out some 20 points. Who is here? What questions do you have? Let me know, and we will start working away. Just let me know. What's up, Dylan? Good to see you. What's up, Brody? Good to see you, Brody. Got a little bit of a toothache today. It's like, I think I flossed too hard, and I'm like, like if it persists till tomorrow, can you help me with number 3 on the summit? It says my PO for the overall model cannot be found, not enough duplicates. Then you need to look at, good question right there, Aisha. We need to look at, we got some of that up right now. Let's go take a look. Can you ask a real question? How would you do the pitch model for the extrapolation? Putting in, so Michaela, great question here. We'll do that next. Still lost on how to interpret the check regression. Go to it. Yeah, let's hop into this. Let's hop into the check regression. Yeah, I'm using floss picks. Maybe I should use like a water floss pick, Brody. Is that what you're suggesting? I'm using like the Crest floss picks where you can hold them. They're super nice, and I must have just gone too hard on my gums. Started hurting yesterday. Still hurts today. Maybe if tomorrow it hurts worse, I'll be like, time for dentist. Woo! And then they'll be like, we'll see you in 2 weeks. And I'll be like, okay. So let's go right here. We got a multiple model. Do not make this one is not one you would do right here. It's got way too many variables inside of it. Let's go ahead and take a look at this multiple model. And what you'll see here is sometimes you can get p-values that are going to not appear. So if you have a p-value that does not appear, you need to go in and start looking at your model. This model is so bad that I'm actually really, let's go change it to weight and see if I get a better, who are you? Who is that person? We're gonna go to a different data frame because that person right there is just making me so mad with the way the values are. They exist so ridiculously, and I'm making models you would not make. Let's do, because my models have variables you should not be using, like categorical variables. And there we go. Here we go. Is it gonna look better now? Let's look at this. Oh, sure. Okay. Let's take a look at this model. Model's got a bunch of stuff in it. Wrapping the screen around right there. Let's take a look at the check regression. And actually we get something we can look at. Okay. So if you get p-values like these right here, the p-values you're getting right here are telling you that you do not have enough duplicate values. These you should not see. These means you've done the assignment wrong and put in a categorical variable. Good thing to point out. These p-values right here, like overall model not being able to compute, which you might also see, we don't see any of the other ones giving the NA. If you get an NA where it just says like NA, that means there's not enough variation. We've just got a lot of categorical variables right here. We go. Wait, ID, good. Not enough duplicates. That is an identifier. I wouldn't use an identifier, but it's saying no duplicate values. This was quantitative. It's just saying there's no duplicate values. It can't compute that. When you go right here, you can see you have the overall model has the NA. So what does that mean we need to look at? What does NA mean for the test? Just explain to me briefly, when it says NA, what does that mean? What is it saying when it says NA for the test? Like what is it trying to tell you about that test? Which the p-value here means we pass the test. This p-value here means we fail the test. Make sure you're very clear. The 0 p-value means we fail the test for the normality of the residuals. The high p-value of 0.636, which is way higher than 0.05, means we pass the p-value, we pass the test for equal spread, which means equal spread is a good assumption to make for our model. The low p-value of 0, which is below 0.05, for the normality of the residuals of the model, means we have evidence of non-normality. No, Dylan, that's a great question. So the NA, what does NA mean? Like when I type NA down here, now it's going to do that. What does NA mean? What is NA? Like when you look at a vector and you see NAs in the vector, well, had to do that, right? When you see NAs in the vector, what does NAs mean? What is NA telling you right there? Just think what that means when you run the test. So if you see NAs in a vector, it means that what's for those values? Somethingness. What does it mean to see NA for vector values? Kind of blank, no data. Yeah, it means missingness. It means it's just nothing there. Nothing to see. So we don't have anything for it. We don't have any values for those positions, missingness, exactly. So what does that mean when you look at the p-values for this test, what was it able to calculate for the p-values for the test right here? What did it calculate for the p-value for the test? The p-value for the test, it calculated what? Look at the p-value and be like, oh, it's telling me that the p-value for the test is whatness. So since we're getting that right there, which some people might get, it's telling you what specifically about your p-value that you just calculated. Just go with the same idea. It's just telling you that. It's not there. It's missing. We just can't calculate it. We can't run that statistical test. It's saying, nah, I can't do that. It's not a pass or fail. It's just saying we can't do that. It's like saying you're playing basketball and I ask you to hit a home run. And you're like, I can't do that. And I'm like, so did you hit a home run? They're like, that really doesn't apply. And you're like, so is the answer no? And you're like, you're asking the wrong question. Our model's like, I can't do this. I guess the technical answer is no, I did not hit a home run. And I'm like, why didn't you hit a home run? You're like, because I can't. I can't run that test. I can't do that thing. So the model's saying I can't run the test. But what we can do for the overall model is look at the plot right here. This is the linearity of the overall model, not this. This is the normality of the residuals. Make sure you know that. But the linearity of the overall model can be judged right here to see if the line goes through the middle of the data. Now, mine's going to look a bit ridiculous, but you shouldn't have as many x's. With the extra equals true on, you can take a look at your individual x's. I do see a little bit of non-linearity right here with weight. I don't know if I see anything else. There's a bunch of the categoricals. Everything's looking good. Not really seeing anything too much. You want to throw this extra equals true on, especially if you have some issues with linearities of individual x's. You won't have this many plots. You should only have 3 x's. I just have a ridiculous amount right here, and it can go through and look at the individual x's. So, and please tell me if you have any issues, especially with knitting. Always knit early, and that's what you have when you have ridiculous amounts of x's to examine the linearity among all the x's. But is this making more sense right here with the check regression? Make sure you're very specific with the p-values on whether or not there's problems. It should be very clear to the reader in almost a concise way on whether or not your p-values have problems. When looking at like this, the linearity for Harry Potter books read is fine. But you should make it very, very clear, when you look at the individual x's. So if we don't have a p-value, we just focus on the analyzing linearity. So if you don't have a p-value, you need to look at the linearity for either the individual x's or the overall model. So if, like, this one, I think weight was a bad one. Fastest car was a bad one. So what I need to do is I need to go back here, and I need to look at fastest car, which is 22. I think it's for some reason... no, it's 22, so they're in order, basically. The linearity for fastest car does seem to have a little bit of an issue. The p-value here is low. So I'd need to comment on this and would say, looking at the plot, I don't see much of it. It might just be due to the extreme outlier at the far side right here, creating a little bit of a nonlinear relationship. You don't have to go into like super duper detail, but it should be clear to you that if you have a problem with this one, you should be looking at this plot. If you have a problem with the overall model, like you can't run it, or any sort of problem, which you notice right here, it says we cannot get the p-value for the overall model, you have to look at this plot. Knowing which plots to look at via this output is important. Does everyone understand right there? So if I don't have a p-value for either of those, that means I did, yeah. And you would comment on that right here. You would comment, does that make sense, Dylan? Up there, you would comment like the p-value for this could not be calculated, so I will need to examine the diagnostic plots. A lot of people skipped over the diagnostic plots. If you can't get the p-value, you're going to have to look at the diagnostic plot. And so, yeah, either the model or log the x, and make sure you're only doing 3 x's. So don't do a crazy model like I'm doing. You're only doing 3 x's. So if you don't have the p-values, you'd comment on that and say, the p-value for this could not be calculated. Thus, I'm going to look at the diagnostic plots to make my decision. And then down here in the diagnostic plots, you definitely need to go into the details related to it. You don't just want to say the diagnostic plot looks good. Is this making complete sense right here? You don't want to be like, diagnostic plots look good. You want to say like, the line going through the residual plot shows a linear relationship. I don't see evidence of curvature throughout. There's 2 clusters here, but other than that, I don't see that the line goes through the data pretty well. Be careful. A lot of people will look at this. This is the non-normality of residuals, which is probably one of our biggest problems. The non-normality of residuals right there is that's a big problem right there. That fails, and that's something in the diagnostic plots that's major problem. So probably my biggest issue here is the non-normality of residuals. Although I see some non-linearity among some of the x's, I really don't think that's my big concern. That was one of the worst offenders. There's so much output. Oh, weight had a very low one. And I mentioned weight way early on. Weight right here, you can see more nonlinearity over here, but it's the bigger concern to me is the non-normality of the residuals. What other questions were there? Let me reappear and let's hop back. Let's talk about those extrapolated values real quick. I think trying to remember, I think it was Michaela had questions about extrapolated values. So if you're wondering about extrapolated values, you can find extrapolated values from your data set pretty quickly. So if you're looking for extrapolated values, you probably want to do a summary of your variable, or there's a few even quicker ways. If you do a range, I might even try some tricks right here. If you do a range on your variable you're using, like let's say I'm using weight as an x variable, you can see the range of the x variables. Anything outside of this range would be an extrapolation of the variable. Does that make sense? How you can do summary of it, you can do range of it. Range gives the min and the max. Summary is just going to give a little extra information. But the range of the x variable is going to let me know when I'm outside of it. And we can use these values up here in our data frame function, which I still should have on the screen. Is it not? Did I delete some things? When did that get altered? I'm going to fix it. There it is. I don't know when I changed that to not be the same thing. Oh, maybe it was because of the size. Maybe that's what it was. But when you're looking at here the range of a variable, if I'm using survey 10 weight as one of my x's, anything outside of this, for 4a and for b, do we just pick any x variables, do the mean, the ones in your model, You'll have 3 x variables in your model. Make sure to not do the variables I'm doing, but you want to do your x variables that are currently in your model. Don't use the model I'm using. Once again, just don't follow my, like Brian's doing exactly this. Extrapolations of these variables would be right here. Like these are non-extrapolated values because the minimum and the maximum weight in the data frame is 75 to 305. So an extrapolation occurs outside of 305 and 75. So that's where we'd be extrapolating. We might, what I'm more interested in, you know what I should do? I was looking at some new function this weekend too. Apply, I'm gonna try something. No. Let me try this. Lapply. Let's do sapply. Sapply, data frame, no, not data frame, survey 10. Survey 10, and let's take, I'm gonna see a lot of people do this now. I'm just trying to think smarter code and using more of the functions I know rather than do things multiple times. And this should only take these vectors. So what I'm writing right here, try to show it in little bits, is a data frame of only those. If you look at this, only what I have right here. Is 3 a hard stopper? Can we have a few more variables if we're using our own personal data? Make a huge comment on that. Make a huge comment at the start, especially so I know. You could be allowed to. Just don't use categorical because we haven't discussed that yet. And so there's some concerns. Don't use categorical. Don't use interactions. I don't think you'll use interactions. But don't do categorical. Don't do interactions. Don't do polynomial. I mean, if you interpreted it all correctly and you did it all, then it'd have to be like, well, they understand this. So, but I don't want people to go to like really advanced topics if they, you know, but multiple regressions, multiple. And we're just handling the linear relationships right now. So we should get fun equals range. There you go. That's what I wanted. sapply is smart apply is what the function is called. It applies a function over multiple things. I probably could have done lapply. It will return a list. So it returns a list now. sapply returned a data frame because it looks at what the object is that I put in, and it tries to return a similar object. I put in a data frame. It returns a data frame to me. Lapply is list apply, so it assumes that I'm giving it a list, so it outputs a list. So we could store this, and this would be objects in a list, or I could store the sapply as a data frame. But you can see here the min and the max GPAs, and this just allows me, what really is great is I could take this same function with the like sapply, and I could run it over all the columns in survey 10, which is just the most amazing thing about like functions is like we go right here Really? Oh, because they're categorical. So we got to see if it's numeric. So let me try two things. I got to for loop it. It's got to be easier than that. So we only want it. Stupid S apply. I don't know. I might stop here. I might keep asking those questions. I'm just kind of, it's mad because it's saying it can't do it for factors. So I want it to, like, if it gets to a factor, to just say, like, no, I'm not going to do that. And then, but it wouldn't, I'm thinking like an if else, but if else, yeah, survey 10. This is going to go through a vector. If else survey 10 equals, yeah. So close. I just need like an is numeric or something on it. And then I could do it with a for loop, and then I'm just like, oh, that kind of ruins it. It's a bummer. There's 7 variables I'm working with. Yes. What? Here, we'll head back to Spice before Brian gets too wrapped up in this one. We'll put a cut. I always wanted to do the S apply on only the numeric columns. And I'm thinking about the code as I like think this right now. I'm just like, how can I get the S apply to only give me the range? So quite a few ways. For 4A and 4B, do we just pick any? Oh, we did that one earlier. If you have questions right now, it's open floor on questions. Open floor. I'm thinking about this S apply. Let me just Google. Someone's probably done it. S apply on only numeric variables. Okay, here we go. Selecting only numeric variables for a data frame. Someone using the S apply right here. Someone's using per, and per is one of the tidyverse things. Select if, dply r, select where. Oh, you people with your select if. Really? So with dply r, we can do select if x is numeric. And so then we could probably make a tibble of it. dply r can probably do this a lot better. Got a few questions right here. I'm still confused on how to do the predict with the extrapolated values. Have you made, so we'll hop back into here. Let's take a look. Have you created, you've got, do you have your extrapolated values? 1, find extrapolated values. 2, like find where you'd be extrapolating. Like where would we be extrapolating? So I found that right here with this. This was my way of looking at it. I know when I'm extrapolating on someone's weight, when I'm extrapolating on someone's desired weight, and when I'm extrapolating on GPA. You could run this repetitively by just going here to range if my code is looking a little crazy for you, and get the range of something like someone's weight, and there's the range right there. I just ran it in a L apply or S apply to get all the values. So do you know where you're extrapolating to begin with? So Michaela, question 1, are you good on that? You know where your extrapolated values are? I don't want to write out all the code. I want to kind of show it. And then if you'll be thinking through. So first, find your extrapolated values. Like I know what values I'm extrapolating on. Like these would be extrapolated values where my model's not going to really be able to make good predictions. So question 1, do we know? Yep, you got those? Awesome. Build a data frame with those extrapolated values. So I'm not going to quite do it. I think the code I have here previously kind of talks through it. I mean, I want you to be understanding what this code is doing, that this builds a data frame of just vectors, of values. It's going to be vectors too. I'll show it here. Those are not extrapolated values. I'd probably call it df2 at this point. So I don't overwrite. I already overwrote though. So do you have this? Have you made your data frame of extrapolated values? Have you made a data frame of extrapolated values, which you could put in whatever values you put in here? If you put in multiple values, you could go right here. I'm just putting in different numbers for the time being, just so we can see different numbers existing here. And you can see you can put in more than one number. You have to concatenate to put in more than one number. And so now you should have a data frame. Awesome. So you see you can put in another row right here. It's just taking these and turning them into, like, you've got a vector right here of 1, 2, and that's people's weights. So when you look at this, this is the first person's weight, the second person's weight, desired weight is 3 and 4, and GPA is 4 and 5. So we've now created a data frame of this where first person is right here, second person is going to be right here because there's second person's weight, second person's desired weight, and second person's GPA. So from here, we're going to use our very similar function. I don't want to write it out 100%, but does it make sense what will change in this code here, Michaela? What you'll change to make this a prediction interval to make 95% prediction intervals using the different data frame we're doing right here. Like, you're still going to feed it the same model. You're going to say a different new data frame because you've created a new data frame right here that has different values in it. And then you're going to tell it a different type of interval you want it to create. And so here we see our confidence interval using the extrapolated values are, oh, I've got a totally different model stored in here right now. There we go. Just, you gotta be careful. If you call everything M, you'll just keep overwriting your model M with different models. But is this, so now we got right here, step 2, build the data frame. So use predict function with proper arguments. How are we looking right there, Michaela? How's everything looking? Do you have the predict function with the proper arguments? So using your predict function right here, just break it down into parts. Always think about it as step by step. I'm going to make predictions using my model because we made a model to predict using those variables. And then how do we plot the regression for individual x's when we check linearity instead of the whole model? X equals true. Check regression. Equal. In quotes. Make sure it's in quotes. Yep, and then make sure it prints what you want. Yep. And that'll switch. If you notice right here, the quick switch between what it gives me, you can see the prediction intervals are wider. This is not the right data set or anything like that right now, but you can see the switch between the confidence interval, which is for the mean of y given some x's. So the much tighter confidence interval right here, which is the mean of y given some x's. And this is not confidence intervals for coefficients. This is the confidence interval for the mean of the line given some... Awesome, Michaela. Keep asking. This is the individual. An individual who has these values, we'd be 95% confident for individuals who have these values to have a value contained in the interval for we're predicting somebody's height right here. The predicted height of an individual is 95% confident to be contained in the interval blank to blank given these values of these x's that we observe. So yeah, great questions right there. And just make sure it's in quotes though, because that one takes a string input. Great job. How are people doing? How are people doing? Keep asking those questions. I can throw code in the chat. Help out. Keep asking those questions. I think people are getting close to done. Remember, when you're stuck for 5 minutes, email. Ask for help. Brian, what's going on right here? My code's not working. So what would you say is a linear graph that is not good enough? So when you look at that, let's pull it up right now. There we go. Let's go look at linearity condition. So of course, all of this applies when the p-value is less than 0.05. That's when we need to take a look at it. If not, and then we need to look at the sample size. P-value less than 0.05, problem. And then we need to say sample size, lowercase n technically, lowercase n greater than or equal to 25. Now we need to go take a look at the diagnostic plots to see what's going on. So you've got, at least you'll have a few different p-values here. I changed it to spacepan. So you've got your p-value for the overall model and the p-value for each of the x's. So if your overall model might have NA, a lot of people are going to get NA maybe. That means you just need to look at it. It means you can't run the test. You got to go look at it. So now let's go right here and take a look at our model. Where do you see the evidence of curvature in the model? At the start, middle, or the end of the model? So where do you see the evidence of curvature? Here, I'll do something even crazier. Where do you see the evidence of the curvature in the model? Also, if P is NA, does it still have to be... Yeah, you would say you'd look at it, yeah. A good question right there, Dylan. If the p-value is missing, yeah, you might just look at it. Really good question. Good theory question. Might just look at it anyways. Where do you see the problem in the model? In the start, in the middle, at the end of the model, or at the very end? And we're only looking at the linearity right here. We're only looking at the linearity. So where do we see the problem in our model? The dip in the middle. That's a perfect way to describe it. The dip in the middle, because we're looking for the line to go through the center, and that dip in the middle is where the issue is at. The other issue you might see right here, which, well, maybe it's a problem. This is going to be the heteroscedasticity. There might be some heteroscedasticity. The unequal plot might show up, but that's not the p-value for linearity. We're focusing right now at least only on, does this line go through the center of the data? So we might say there looks to be some problems right here, especially towards the center of the model, where the linear relationship is not going through, like the line does not do a well job right there. Now, when you look at your individual x's, like this is here your x1, your x2, and your x3, you might see just differing types of relationships where, you might see like this right here. That's perfectly fine. Just a little bit of a grouping on it. So where are we going to see, where do we see the problem with linearity right here? Which one, x1, 2, or 3 is where we see the problem with linearity? x1, x2, or x3 do you see the problem with linearity? So if you're looking at this right here, where do you see the problem with linearity, x1, or x2, x3? Which one of these graphics show linearity? And p-values for these would probably be something like maybe... Yeah, 2 has the same sort of dip in the middle, and that might be where our relationship is coming from up here. A lot of times you'll see a graphic in X variable that kind of has a similar relationship to... I feel like I'm too far over on the screen. Let me grab my camera right here and move it back. You'll kind of see some similarities among X's where they're doing kind of similar sorts of things. I think the camera got moved. I think it did. Whoop, look at that. Well, that's going to change. Let's hope this doesn't mess everything up. I'm going to be reorienting stuff right here. So, I don't want that much. Sorry, I'm doing a little housekeeping right now. Got to lock that. Oh, no. Oh, my God. Changing my camera size right there. Let me take that right here. Mikhail says... How do you know? And then, so Trace said first, how do you know what to pick for the extrapolate value of each variable? Check out just a moment ago, Trace, we were going over how to do the extrapolation. Probably about 10 minutes ago, you'll see I was working on that. So check out those portions of the values right here, talking about how to do the extrapolation and to how to find extrapolated values. Tell me if you're stuck on that and we can do it again. But we were going over how to find extrapolated values, like when are we extrapolating? So check that out right there. I'll hop to Spoice. When I run the predict function for the extrapolate values, I only get one line for values for... Yep. Because if you have 3 x's, then you're just putting in a value for each one of the x's. So you're just making a prediction for a new individual. Like they have a height of this, a weight of this, a desired weight of this, and we're predicting their GPA or something like that. So you will just get one line of code with the prediction, which is the fit. The model itself would make a prediction, and then you'll have a interval to predict what the individual might be between. Like I'm 95% confident this individual, an individual with these values would be contained in the interval blank to blank. Does that make sense, Michaela? You will only get one row. Do we have to get the range, or if we know our data well, can we just hardcore it? You could just explain. I can always take a look. If I don't feel like you extrapolated, I might ask a question. Like if you're predicting people's height and you put in a weight of 180, I'll be like, it's not an extrapolation. You'll be like, oh, but it's second graders. And I'll be like, even then there might be a 180-pound second grader. I don't know. Maybe the data doesn't have that. But I would need to kind of see, you don't have to make it, it's pretty obvious. Like if you're doing, just don't go crazy. Like I'm predicting someone's weight who weighs 1 million pounds. Well, yeah, that's an extrapolation. I guess I got to count that. So with those values we choose, it tells us the interval for the y, what we estimate. Is it making sense, Michaela? I'm really glad. As you're doing this, being it's saying if we have these x values, then here's what we predict the y value for a person with these x values, like an individual person. Stock daily percentage change is what I'm working with. So it's like an extrapolation of a 99% drop. Yeah. There you go. There you go. 99% drop. Woo! Crazy drop. Yeah, just maybe explain that to me just briefly. Help me out with that. Michaela, excellent work. That's what I want to see. I want to see those things clicking as we just like work on it, talk about it, and you look at it. Just keep asking those questions. Let's throw some 50 points. These things are not something we learn in a day. You should have saw me my first semester teaching this. I've seen 70% drop in one day, so it's definitely possible. Or theoretically, you could say, right? Like, you've never seen the 99% drop, but you could say, you know, theoretically, we could see a 99% drop, and our model currently doesn't have data on this, but extrapolating from what we believe the model is, but then you gotta be careful because it's going to cause more uncertainty. You're already predicting for an individual. Yeah, but no, you would just tell someone this, be like, well, this is outside the bounds of the data we currently have observed, making an extrapolation. So the model's going to have like added uncertainty in this prediction. Extrapolating on the data. Is it we end on Tuesday? Is Tuesday our last day? My God. I can get my second and third Pfizer shot. I can get my second Pfizer shot on next Monday, 3 weeks out. And I'm just like, I don't think I should. I'm going to probably get it on the Friday because you just have to wait at least 3 weeks. I was talking to them about that this morning. And I'm like, I don't know if I should get it like the last 2 days of our class. And then I'm here and I'm like, hey, everybody, I feel like bleh. I don't know if anyone else has gotten Pfizer besides me and has had any reactions or anything. I got little striations on my arm, like little just tiny lines, and I was like, that's cool. Not cool, but perks of being high risk. I got mine back in April. Way, well, I'm sorry you're high risk, and I'm glad. Did you get Pfizer? Well, if you want to talk about it, your call. Always your call right there to talk about such things. But yeah, I literally slept 18 hours straight from. Oh my God. I think I'm gonna be getting it on the Friday. And then people are going to be like, man, Brian, where's our assignments for this week? Why didn't you do any grading? I'll be like, I was out. I went back and found it, but when I run predict, I get 2 different intervals. Do you want to send it to me on the Discord, Trace? Take a quick look right here. Pfizer, and it destroyed me. One more question. How do you phrase the 95% confidence interval for the mean of the X's? I am 95% confident the true mean of the X's. I am 95% confident that the true mean of y, when we predict for the mean of the x's, would be contained in the interval blank to blank. I am 95% confident the true mean value of y, which is where the line would be at, you can put it in parentheses. I am 95% confident the true mean value of y, which is where the line is at, would be contained in the interval blank to blank when making a confidence interval for the mean of the x values. Just I am 95% confident the true mean of the y, which is where the line is at, is contained in the interval blank to blank when making predictions for the mean of the x values. Standardized interpretation from Stat Tool 1. Does that make sense, Michaela, right there? I am 95% confident the true mean value of y, which is where the line is at, is contained in the interval blank to blank for the mean of the x values when we make predictions there. It's weird to say prediction because it's a confidence interval for the mean of the y value. So all that good stuff right there. Perfect. Boom. Got it. Yep. Stat Tool 1 interpretations can help sometimes. Send you my code. Let's take a look at that code right here. Asti Trebru. Is that you said? Okay, here we go. Code. Do I have your permission to show the code? Yes or no, Trace? Well, let me not show it too much because I don't want... This is looking great, Trace. What'd you say the problem was? This is looking really great right here, Trace. From what I can see... Put on a little more music. Your code's looking great, Trace. Not glad this class will be done, but so looking forward to next Wednesday. Have a class on campus for the first time since March 2nd, 12th, 2020. I'm thinking about booking a trip to campus here. Flying into campus. Want to do something with... why can I not think of the place downtown? I can't think of it. Cruise farms. I want to do something with them, if they would. Maybe they won't. Trace said... I get 2 different intervals when he runs predict. Okay. Let me run all your code, Trace. Okay. And then always try to make sure everything knits. Like, oh, looking pretty good right there, Trace. Okay. Oh, I see what it is, Trace. You might have... Yeah. Okay, I see what it is, Trace. Okay, so Trace, how many individuals did you create? And I see what you did. Which your mother's weights values, one of them is not an extrapolation. Actually, some of these are not extrapolated values. Oh no, maybe my brain's breaking. Let me look. No, I think. Wait, my brain is breaking, Trace. No, I just ran the lapply. Here, I'll point to. I'm gonna send it to you on Discord. You only need to put in one of these, and here I'll circle the ones that are extrapolation. And I'll send it right back to you, or I'll highlight them. Or are those other ones the mean of the y? Are those first ones right there, like the 129? Are those? I think those first ones are the mean of the y, right? I mean the x's. Hiccups now. Let me look at this. I think you put in the mean of the, which is fine. Yeah, you did. That's all right. That's all right. Yeah. I'm just like talking to myself. So yeah, what you have right here, Trace, is your second. So your first interval, the mean and the extrapolated values. So you can do it. And you could only. I'm going to show you something right here. I'm going to put this in the chat. And I want you to think about what this code is doing. Here, Trace. I want you to look at this code in the chat. And I want you to think about what that's doing right there. So that'll get you just the one for. I think you should see what it's doing, because the first values you put in are the mean of the y's, and the second value you put in are the extrapolated values, which is a perfectly fine way of doing this. And if you only want to report that one interval when you create the output, you could just run that right there. And does that make sense what that's going to do then? All I added on to the end of that code, which you currently have, all I added on was that right there. That's all I added on to it, just to be like, let's just get this one part of it. So since it's a two-dimensional object, just think about what I'm grabbing from it. I'm saying, okay, it's a two-dimensional object, hence we got the comma right there. If you have more questions to ask, and people ask away, feel free to ask. I'm trying to think when I do the review for 201. Let me double check the channel right here. If you have questions, let me know. Great job, Trace. I'm going to close out of your work, but I see what you did right there. I was so confused because you found extrapolated values, and then I was looking at it, and I was being like, wait, where are these And I was like, oh. Might have a lot. We got 10 people watching. If you have a question, let me know. Review for 201's not for a while. That makes sense. Awesome. Returning the second row. What other questions are there? We got a bunch of people watching right now. What other questions are there? Say hey if you're in the chat. It says 10 people watching. Who's all watching? Let's put on Celeste. What question are you working on? What are you stuck on? Let me know. You can ask in generalities. A lot of good work. Okay, just to clarify before I head out, if we have NA, no duplicate values for a variable, and the model for linearity, yeah, that's what you want to do. We were talking about this earlier. I'll show it again just so people can see. So when you're running these tests, sometimes you'll get back an NA. NA just means that it's missing. It can't perform the test. So when your p-value, so with the practical distribution model, we would just... here, I'll talk about that next, Michaela. Good question, Michaela. Definitely great question. Kind of. It's kind of more it's almost the exact same thing from last assignment. So the NA right here, the NA means we can't run the test. We just do not have enough duplicate values, which this data set actually looks like it does have enough duplicate values, but that's besides the point. So you would look at this right here and see that there's a violation across here. Down here, you maybe get all the p-values. It's possible one of these could come back with NA also. If this comes back with NA, it doesn't mean it failed. It just means you must visually examine the plot. Like at that point, you're stuck and you're going to a visual examination. I would say no matter the sample size, at this point, you do a visual examination because it doesn't mean you failed. It just means the test could not mathematically be performed. That's what the NA means here. This one failed. This one right here had a p-value less than 0.05, let's say. So all of these have failed the test. This one right here, I'm not so worried about. Just there's got a high point up here, so maybe that's why I pulled it away. But overall, the line looks to cut through the center of the data. So we're gonna add a nice green line right here to be like, yeah, you know what? You did pretty well. Now this one gets a red line and probably where the relationship is coming from because it's getting that sort of like non-linear relationship. So if all the graphs look good, the model's good, means the model's a reasonable reflection of reality. Is the model good? Is it practically significant? Is it statistically significant? Not something for the check regression to find. Dylan, great question right there. So just passing these conditions right here, which that's got some heteroscedasticity, but it's fine on the linearity. Yep. Great job. And then we can do that next here. Great questions, everybody. So remember, with the p-values, if you get an NA, that just means we can't run the test. Bad? Yeah, maybe. And then Mikhail was asking about statistical significance. Okay, I mean practical. Let's go ahead and look at a model right here. Give me half a second. Someone pull up a model right here, and I want to know if this model is statistically significant and practically. So this kind of goes towards the end of it. Statistical and practical significance is what we're talking about here. See you tomorrow, Dylan. Excellent work. So this goes towards the end of the assignment when we're talking about statistical and practical significant. What does it mean that GPA is not statistically significant in this model? So when we see right here GPA is not statistically significant, what does that tell us about GPA? Versus when we see weight is statistically significant in this model. So we have individual coefficients and their significance. No one cares about the intercept because that's just an arbitrary value of where all the x's are equal to 0. And then we're saying, well, do we have evidence that the value of y is not equal to 0 at that point? Sure. Cool. Intercept, you're a value. You exist. But what does it mean that weight is statistically significant in predicting someone's height? And what does it mean that GPA is not statistically significant in predicting someone's height? That's also a part, and then we're going to do the practical next of this. And you might mention some R-squared adjusted. You might go a little into R-squared adjusted right here. Next assignment's going to do some more variance inflation, some other topics. So expect some variance inflation stuff in the next assignment for multiple regression part 2. So what do you have right here? So the model itself is statistically significant, and we see that down here. Very important to know where your statistical significance of the model is. It's done via the ANOVA test. Now, we don't need to run the ANOVA ourselves, but the ANOVA test is done down here at the very bottom for us, and so we actually get that output, and there's the p-value for the model. So the model is statistically significant. The model is statistically significant, which means the reduction in the sums of squared error from the naive, which is a no-variable model, is unlikely by random chance. So the model is statistically significant. But what does this having a high p-value tell us? And what does weight having a low p-value tell us? Very important. This is on the assignment. And then we're going to do practical significance next. What do those p-values tell us right here? Like GPA has a very high p-value. What does that mean? Weight has a very low p-value. What does that mean? Like, what is going on right here? What's the deal with those p-values? What the heck? What do those p-values tell us? What do we know about weight? Low p-value. What do we know about GPA? High p-value. If new information is brought to the table by each variable, exactly. Like when it comes into this model, is it bringing with it new sources of information that are unlikely due to random chance? And when you look here at the p-value of weight brings with the other variables already in the model. Like weight shows up to the party and it's like, hey, I brought $100 bills, and everyone's like, you are awesome, weight. And then GPA shows up and they're like, I brought pennies, and we're like, yeah, we don't really care for that. And they're like, but it's pennies, and we're like, you go away. So when we look at what this brings to the model, it brings new significant information. And kind of that it's a good predictor. But be careful though. It's not by itself. And this is the big thing, Michaela, so make sure to stress this in your assignment. It's not that weight is a good predictor of height by itself. It's when it joins the multiple world, which means it joins into a model where all these variables are at the party. Just always think about it as a party, and weight shows up and it's like, hey, everybody, I brought Papa John's pizza. And people are like, hey, that's cool. And then GPA shows up and they're like, hey, I brought Little Caesars. Now people might, well, actually, you know what? Weight shows up and they're like, hey, I brought Papa John's. And then desired weight shows up, which is interesting that they both work so well in the model together. Desired weight shows up and it's like, hey, I brought Hard Knocks pizza. And you're like, oh, that's awesome. And then GPA shows up and they're like, I'm thinking of something really lame to bring. I brought croutons. And everyone's like, I don't think we're going to be eating croutons. We got Papa John's pizza and we got Hard Knocks pizza. And you brought croutons? We don't have any salad here. But if someone had brought some salad, then maybe GPA would be significant because it's kind of like adding to the model where other things are not doing things. But right now, GPA is not doing anything good for us in this model. It's not bringing new information that the other variables are not accounting for. It might not even be bringing good information at all. But GPA is just not helping out this model with the other variables already existing. Weight and desired weight probably have some overlap between each other. Just to mention briefly something we talked about today. That is not what I wanted. So weight and desired weight do have a lot of overlap. They have a high variance inflation factor, probably due to each other. And so even though they're overlapping in the variation they bring, they're still bringing enough new information. And that's the important thing to look at right here, is to know that weight with the other variables in the model, and this is the important thing right here. So weight with the other variables in the model is bringing enough new information to help out. GPA is not bringing enough new information with the other variables in the model. So is true or false? From this output, we know GPA is a bad predictor of someone's height. From this output alone. I've just sneezed so much today. From this output, we know that GPA is a bad predictor of someone's height. And GPA does not predict someone's height very well. We would know that from this model. True or false? Hopefully I don't trick too many people on this. Like, wait, is it a trick question or a trick question? GPA is a bad predictor of someone's height by itself. GPA. Correct, Trace. You would know that all your individual variables are bringing with them new information. That does not mean the overall model is significant, though, which is weird. I think in most instances it will be. There's paradoxes. There's things that are just weird in statistics. I think that's like a super weird thing if you see like all your p-values are significant. So GPA by itself, true or false? It should be. Logically, it should be, but then just statistics is interesting. So true or false? Yeah, it'd be really rare, but you can get weird stuff in statistics that apparently the overall reduction in sums of squared errors is not large enough to be unlikely by random chance, but the p-value for each x variable is low, meaning each variable does bring with it new information. Well, I wouldn't say that it's not a good predictor. Be very careful. It's not that it's not a good predictor. That's kind of the trick right here, and the thing we need to highlight. GPA could be an amazing predictor, but then this is what we keep going over right here, just to make sure everyone gets it before we do some practical significance. GPA could be an amazing predictor. It just means what when you see that p-value? GPA could be one of the best predictors we have. It could be like weight and desired weight together. GPA is doing all that work, but GPA is not bringing new information to the model. So it's not that GPA is not a good predictor, and actually I think it is also not a good predictor. We don't know that from this output alone. How could we analyze if GPA is a good predictor? So this is a great question, a good essay question. How could you analyze if GPA was a good predictor of someone's height? How could you analyze if GPA is a good predictor of someone's height? Just focusing on that, something we've done before. How could you analyze if GPA, just in and of itself, that's kind of the hint right there, is a good predictor of someone's height? How could you analyze if GPA is a good predictor of someone's height? Yep, that's exactly it. That's exactly it. So now we can see if GPA alone, and GPA does have significant information. GPA, that is so funny right there. I didn't expect it. Exactly, make us. So GPA by itself is statistically significant in predicting somebody's height, but in the multiple world, it does not bring with enough new information. If you look, GPA was only bringing like 2% of information. That overlap is apparently, maybe there is some overlap. There's really not much overlap. It's just not doing enough in the multiple world. That 2% is dwarfed by this combined 60%, like weight and desired weight. We could go make that model. Just going down here, we could look at weight and desired weight by themselves. And you know what we could do? We could kind of branch topics here and start talking about the practical. So here's weight and desired weight is 62.18. When you throw in GPA, it's 62.18. And now it's 62.21. And I want you to look at this. What do you notice happens right here when you add in the third variable? Can I get it both on the same screen at the same time? So for 5B, we're just using conventionals to answer the question, or are we using p-values too? Let me look in 2 seconds right here. We'll do that one next, Michaela. Great questions today, Michaela. Thank you so much. And we'll finish practical stimulus, and we'll go back to 5B because I think this is the last part of the assignment. What do you notice right here, which is something we talked about today? This is the 2-variable model. This is the 3-variable model. This is a great review of today. 2-variable model, 3-variable model. That's correct for this. The model is down here. That's the model. So this model is statistically significant. This model is statistically significant. What do you notice about the R-squareds adjusted when you go from the 2-variable model to the 3-variable model? What happened to your R-squared adjusted? Here's the 2-variable model. Just look very carefully at that. And then here's the 3-variable model and look very carefully at that. So what happened from the 2-variable to the 3-variable when you went to your R-squared adjusted, which is a very good thing to look at. That'll definitely be coming up more on assignment. It gets smaller. So that was a bad idea. What happens to R-squared every time you add variables? This is why we don't use R-squared a lot of times in the multiple world. And this is just a more fairer assessment of how we're doing, and we can use it to compare models. Very good model comparison saying, yeah, I'd probably go with the 2-variable model because, well, one, GPA is not statistically significant, and also the R-squared adjusted here is higher because this is the penalized. Yep, and R-squared is always going to go up because R-squared, depending on how many variables. And so here we'll finish off with practical, and then we'll go to Michaela's next question. Thank you so much. I'm sure this is going to help a lot of people. When you look at this, and you know what? Practical significance compared between these models, a really great measure is RMSE. RMSE is the what of the model, the typical miss. Which model? Ooh, actually, it's super close. They both basically have the same typical miss. So do we need to make a 2-variable model? No, yeah, don't worry about that. You can just keep to the 3-variable model. So the typical miss this model makes when predicting someone's height is usually about 2.738 inches. So that's going to be the practical significance right there. Also, the R-squared tells me practical significance. So your practical significance, to directly answer Michaela's question, practical significance is going to be these values right here. The main point of this right here is model comparison. Does that make sense? Like when you look at your output, don't worry about the degrees of freedom. Just don't mention that stuff. That's statistical calculation stuff. The residual standard error, which is the RMSE, is the typical miss the model makes. Make sure it's in units of Y. When predicting someone's height, I typically miss by about 2.738 inches in my prediction. And then the R-squared tells me 62.21% of the variation in someone's height is explained by my model. 2 seconds right here, everybody. I'm back. So with this right here, that makes sense. Awesome. And here we'll handle the other question right here. Let's go back. Click on buttons. Michaela's other question was, so for 5B, are we just using confidence intervals to answer the question, or are we bringing the p-values too? So I don't want to be too specific, but let's take a look at some 5B. Here we go. Let's take a look. And let's take a look at that. Explain how you know your model is statistically significant or not. How do you know, and what are we looking at to know if our model is statistically significant? How do we know our model is statistically significant, and what are we looking at? So maybe I got some hints on the screen right now. How do you know your model is statistically significant? You go into details explaining it, but it needs to be pretty clear, and I would cite a value. Like when I read your answer, there's a lot of ways to answer this, but how do you know your model is statistically significant, which is something we went over in the notes today especially. We went over to also thing on Friday. P-value on the F statistic line, exactly, which means the reduction in the sums of squared error from the naive is unlikely by random chance. It's like all the variables coming together. That's what the ANOVA does, is it looks at everything coming together and seeing how it does all at once. So let me type something really quick right here. 2 seconds. There we go. And then how do you know if individual variables are statistically significant in the model? Now, this is something big we've been covering. So you can look at the confidence interval, but how are individual variables? I mean, there's a few ways to describe it that I'll probably be nice on, But, you know, you can run the confidence right here. But how are these individual variables? Like, why would something be statistically significant in the model? So, like, just think through, like, what we've been talking about. And, you know, there's a few ways to talk about it. Exactly. And then the p-value right there denotes whether or not they bring new information. And that's the how something is. Like, not is something, they're individual p-values. And so yes, and then what does it mean? Like, how do you get a low p-value? Like, I should have gone into more detail. Like, I maybe could have been more specific. I've kind of been answering it a lot today. That it's all about that new information, that this model brings with it new information that is unlikely, or the variable brings with it new information that's unlikely by random chance that the other variables are not currently accounting for. So this right here is super, super important. Awesome. Is that making sense, Michaela? How to answer these? Write a short summary on why you believe your model is or is not practically significant. Please cite values. Please cite values. I think everyone has looked at my grading and knows that if you don't cite values down here, and if you're just like, here's some things to not, let me cut the video right here and switch. I'm going to talk about a few things right now to not do for the last part. Let's just throw in some hints right there. And these are related to things I've seen. Do not, I mean, you could just say my model's not a good reflection of reality. Wasn't there a comment in the notes about R squared and R squared adjusted values being close to each other? That's the closer they are together, Michaela, then the less junk your model has in it. What you're going to see when your model gets junk put in it, like variables that just don't help out, is they're going to drift away from each other. Like your R squared is going to go up very slowly, and your R squared adjusted is going to start to like go away from each other. So the closer they are together, the better. So you could mention that. These are fine things to mention right here. Like we're mainly looking like at RMSE, mainly looking at R squared. So you could do an R squared to R squared adjusted comparison. Let's throw some 20 points right there. I think that's such a great thing to mention. Like, you know, saying you could literally find out my R squared adjusted is this % of my R squared to talk about. Why not 50 points? Why not? I think that's a great thing to mention. Like, it's how you could incorporate this right here to not use it as a model comparison because maybe you don't have model A versus model B at this point, but to talk about like my R squared is very close to my R squared adjusted, or my R squared adjusted is very close to my R squared. So the inclusion of all the variables is maybe necessary because the R squared adjusted is just going to be our penalized R squared. So we're just adjusting, like focusing on that adjusted word right here. We are adjusting R squared for how many variables are in the model. So all of that good stuff right there. What other questions? But the check regression is not super important to talk about right here. Yes, it would tell us if our model is a reasonable reflection of reality, which is a good thing to talk about. But at this point, we're focusing more in on like, how much does our model usually miss by? How much of the variation do we understand? We could probably, if we knew AIC, we could talk about AIC, talk about how close our model is to the truth. There's some really great things to talk about here, but you don't really want to focus in on like check regression at this point because that's not going to be so helpful. What other questions are there? Put on a little music. Which one have we not listened to? Let's do this one. Nice little chill music right here. Let's go back. What questions are there? I feel like people, how much time people put into this assignment, and are you almost done? Can you go over the interpretation for 4B? Let's talk about that. Let's head back over here. So when we do 4B, we're talking about the extrapolated values. So we're talking about, you know, I am 95% confident that an individual, there's the difference right here. Prediction intervals are for individuals, where the confidence interval, it says for the mean of the x's values. Confidence interval, even though we're doing mean of x's, is mean of y, which is the line. So this is what you're making predictions on right here, and I think we can do a trick. Watch this. But yow. There we go. And this is for individuals. So when you make this, I am 95% confident interval, that an individual with the extrapolated values would have a y value contained in the interval blank to blank. Does that make sense right there, Trace? I don't want to say it too specifically. I think maybe if you listen in, you can kind of throw your words into it. But like I am 95% confident, an individual who had these extrapolated values of x's would have a y value contained in the interval blank to blank. So it's like set to one pretty much, where you say I am blank percent confident that the true value of an individual, so we can say true value of an individual's height, if I'm predicting their height, would be contained in the interval blank to blank when they have these extrapolated values of the x. Does that make sense right there, Trace? I think people are doing a great job. We're pretty far into this week. Oh. My fiance is getting some food. I'm excited. We'll hop over here. Trace, I did something this week and I looked. Keep asking those questions if you have it. My fiance is getting me some ramen, I think. She's at an Asian market and she's getting me some ramen, I think. And I love ramen. It's funny. I don't like the more fish ramen flavors. Like, I don't like fish eggs and stuff like that. I don't know. I've never roe. Just no matter where I've been, I like a lot of like sashimi, other things like sashimi. I absolutely love, but just fish eggs. I don't know. I've had it multiple times. I'm just like, I don't like fish eggs. Squid, sashimi. I know sashimi could be squid, I guess, but different things. Sushi, obviously. Love all that stuff. Man, you put some wasabi on some sushi, a little tiny bit of soy sauce. Oh my gosh. Haven't had sushi in forever. Be amazing. Some salmon sushi. Crab is usually not crab though. Crab is usually some sort of fake. Chuyong, we went to a restaurant, a Chinese restaurant, and we were ordering sushi, and Chuyi, my friend, said, he goes, "Is this real crab?" And the person goes, "Yes." And he goes, "No, is it real crab?" And they're like, "No." And he's like, "Okay, I don't want it," because apparently it's like they don't use real crab. Like, not. It just depends where you go or something. But we like asking, we were like, "What do you mean?" He's like, "A lot of places don't use real crab." And we were like, "Oh, really?" And he's like, "Yeah, it's like a crab substitute meant to taste like it." So it's like, I wanted to check before I ordered, and I was like, "Oh wow, I didn't know all these things." But I miss that. It's one of the things I miss about going out and doing stuff. But Trace, I looked up some 5K races, and I was trying to find out when I turn 40, I want to run a 5K or something and try to place. And I think I need to go sub 19 minutes to have a good shot at placing. Like, I need to be in like the 18s. And I saw my old cross country coach ran a race when he was 40 on the dot. Continue my interpretation. Yeah, send me interpretation. I'll take a look and I'll be like, yep. So I looked at my old cross country coach's times, which I'm never going to be as fast as him. And his times were like 17:40 or something like that. And he was doing that at 40. And I was like, I'm not running. I think it was like a 5:40 pace. I did run pretty fast a few days ago, though. Or no, yesterday. I've been timing myself. And I'm like, I am not going to be able to run that time. I'm not going sub 18. I say that, and then a year from now, I'm going sub 18. I think most people do 5Ks around the 17 mark, so 19 would definitely be a good time. You mean most people do it around the 17 mark? Are most people around 17 minutes? I mean, maybe like most 20-year-olds, or maybe like good runners, like good 5K runners in high school. Like if you're like on a good cross country team, I think 17:12 was my best time ever. I wanted to go into the 16s, but when I got into the 17s, you break 20, and that was a big accomplishment for me. I was like, oh, sub 20. And then I got like some 19s. I was like, oh man, I got like an 18. I was like, dude. And then my 17 came out of nowhere pretty much. No, I think it was 17:24. I used to have like a screen name. That was my cross country time. That's how proud of it I was. But I went low 17s. And then my coach, so for your age range, 19 minutes would definitely put you in contention to win. Yeah, I'd love that. I got to be around a 6-minute mile pace at that point. I got to be like, which I'm trying to, I've been going out and running only for like, what I do is I run really hard for, I have this one stretch of land I run, which I've measured to be about 1/7 of a mile, and I do it in about 40 seconds, which means, how fast am I doing it? Yesterday I did it in 42 seconds. I was really happy about that. So I was running that at 6-minute mile pace. No way. It's gotta be longer than that. Because I was tired when I ran that at 6-minute mile pace. Sending rotation. Let's take a look here. Need to like go to a track. I know. Gestation wouldn't be 70 pounds. Gestation would be 70 weeks. Oh, and it's not in pounds. It's in, here, I'll make some corrections. I'm making corrections to yours. I think this is in grams. Is it? Let me. It's, or is it ounces? This is the birth weight. Oh, yeah, it's in grams. It's in grams. What the heck is a gram? So. There we go, right there. It's gestation is how many weeks did you gestate, which is how long did you carry the baby. So I did some. Whatever. Yep, that makes sense right there. So, and then the 7,000 is the point estimate. Like if someone said to you, like, so the 7,000 is not the truth trace. Does that make sense? 7,100 is not the truth. That's just if you had to make like a very exact prediction. If someone's like, give me an exact number, you would say 7,100. That would make sense because I was like, yeah, it's ridiculous. And that's because you're extrapolating well beyond. Yeah, and 7,000 pounds would be ridiculous. I think 7,000 pounds is something like 7,000 grams is like 13 pounds. And 13 pounds is a ridiculously large baby, but we're extrapolating. In a 70-week gestation, that's the woman is pregnant for 1 year and like 3 months, 2 weeks in a year. That's 1 year, 4 months, I think. So you're saying, given this information, things like, you know, the woman weighs this, and she's pregnant for 1 year, 4 months, which now is just ridiculous. So like, well, that doesn't happen. Like, longest pregnancy ever. There's got to be something crazy right here, right? Longest pregnancy ever. The longest pregnancy ever. Someone was pregnant for over a year. Found it incredible that Miss Hunter had been pregnant 375 days instead of the normal 280 before her baby was born. Their last week. 375 days, the longest pregnancy on record, topping the runner-up by about 58 days. 1945. Maybe they got it wrong or something. But 1945, someone was pregnant for 375 days, over a year. Over a year. So that's your number right there of 70 weeks is an extrapolation even beyond the 54 weeks or so that woman was pregnant. So that's your number goes, which is the point of this, to go well outside of the model. And then see the model does not have a good, reasonable reflection. We played that one just a second ago. But I think that's got it. I'm going to take a little break here before I stream for 201. Any last questions here before we head off? I think we've done it. How's the assignment going, Trace? Should be pretty good. Should be making sense with what we talk about in class. Going to send my data into the Mayo Clinic. Be like, just in case women are pregnant for 70 weeks, here's my model. Here's my predictions. And they'll be like, what is your teacher teaching you? How to extrapolate, that's what we're teaching you. But we'll be back, or I'll be back here talking some 201. You can always swing by. It might be really super slow. You never know. Feeling pretty great about it? Awesome. Well, we'll be back here. Puppet Shark. We don't see you during class. I'll see everyone later. Bye for now, everyone. Bye.